Alright, so for this video I have a fun idea. So some people complained that RNNs and LSTMs are not complicated enough. So in this video we are going to make them a little bit more complicated. So in particular we are going to talk about recurrent neural networks with a so-called attention mechanism that helps it dealing better with long sequences when we have tasks such as language translation. So just to recap how language translation looks like. So this is a many-to-many architecture for language translation. So we have an input sentence, and this input sentence gets parsed into one hidden state. So this whole part is essentially encoding the input sentence, which is why it's also sometimes called as the encoder part of the RNN, similar to how you call the first layers of an autoencoder the encoder, because it's compressing the input into one, let's say, hidden state. And then we have this decoder part of the RNN, which takes in this hidden state and then produces the translated sentence. If you're interested in playing around with an example, I haven't made one for this class, but there's an excellent tutorial here on the PyTorch website that you can check out. But before I show you how the attention mechanism works, let me give you an example of a language translation task. So here I'm translating one input sentence to an output sentence. So the input sentence is the English sentence, "Today is a great day." And I'm translating it to "Heute ist ein großartiger Tag." So I'm not sure if you can guess which language it is. Maybe a fun question for Piazza. In any case, one thing in this particular sentence is that it actually translates word by word. So if you would take a dictionary, you could technically just translate it word for word. So if you have a sentence like that, you could almost use the many-to-many RNN that we learned about in the previous lecture, the one where we have the inputs, then the hidden states, then the outputs, and we technically could just have the setup like this, like a many-to-many setup where we are translating word by word. But this doesn't work for all sentences. So this is why we have this delayed setup where we usually don't have these parts. And this one goes into the decoder. And the decoder then produces the outputs just based on the last state, because for some sentences there's not this one-to-one correlation between input and output word. So for instance, here's another example sentence. It's, "If you have ever studied a foreign language, you have probably encountered a false friend at some point." And here, this is the translation. So one thing that happens is, for instance, this one, these two words become one word. It's called Fremdsprache here. And another thing I can spot here is that the you have, and here also, it translates one time to this word. So actually the combination of these two, which are farther apart. And then for this one, there is no corresponding word really. And this one corresponds to this one. So in this way, here it's not so obvious, like we don't have this one-to-one mapping. So things might be shifted a little bit around in that sentence depending on the grammar. So it's not super straightforward to use an architecture like the original one that I had before here, because we can't just map input to output. Which is why we have this setup, this many-to-many setup, where we have the input sentence that gets parsed into this hidden representation, and then we have something that creates the output, so the encoder and the decoder network. However, then one challenge is really that the network has to compress all the information into this one hidden state, right? So essentially it's like reading the whole sentence here. It's reading the complete sentence, and after reading the sentence, it's starting to translate. So how do we make sure that the network even remembers, right? So if it reaches this point, it has to contain all the information of the whole sentence, and this can be actually quite challenging. I mean, even for instance for you, if you think about a sentence like this, it's maybe easy because it's just 4 words, so you can memorize them and then translate them. But let's say you have a longer sentence like that, and I read this out loud, and then I tell you in 1 minute you have to translate it, but you're not allowed to look at the whole sentence anymore. So in that way, I think also you would have a challenge memorizing all the words in that sentence, because it's a lot of words. So same for the RNN, it will probably be challenged to have all the necessary information in this hidden state the longer the sentence becomes. So this is why researchers worked on this so-called attention mechanism to address this issue of having poor performance on long sentences. So here, this is going back to the paper by Badenau and co-workers, and as far as I know, this is the first paper that really proposed this attention mechanism, but I may be wrong. There may have been other papers, but this is at least the first one I am aware of. And the key idea here is essentially that it's a mechanism that allows a model to automatically soft search for parts of a source sentence that are relevant for predicting a target word. So if I go back one more time to my sentence here, so let's say it's currently at that point translating this sentence. It's allowed to look like in the original sentence which words are most important. So it has access to the whole sentence at each time step, essentially. That's the idea. And some words are more important than others. So for instance, this might have a very low attention, like 0, and this one is kind of relevant. It has maybe attention close to 1 if we have an attention value between 0 and 1. So we have high and low attention for different words. But at each time step, the model will be allowed to take a look at different parts of the sentence. That's like the new idea here. And at the bottom here is an illustration of how they evaluated the performance. So there's something called I think it's called Blue Score, and this is a score for computing how good the quality of the translation is. So we won't go into too much detail of how that works. For this lecture, just assume a higher Blue Score is better. So this is better if it's high. And what you can see here is the sentence length. So they did experiments with different sentence lengths, and you can see that for these two networks, these are abbreviated RNN-30 and 50. So these are essentially encoder networks, like regular. They're actually traditional RNN networks. So it's just like a shortcut for these networks. And the 30 and 50 is how much access they have to the input, I think. And you can see that the performance drops dramatically for sentence lengths larger than 30. So you can see it gets good performance in this region, but if you get longer sentences, longer than 50 words, then the performance declines. But when they use this attention mechanism here, they get good performance even for longer sentences. So here the takeaway is that they find that the performance for longer sentences is better if they use this so-called attention mechanism. So how does the attention mechanism work? That is what I will show you in the next couple of slides. So as I mentioned before, for each word there will be a certain context provided, so the network will be allowed to look at the input sentence and see which words are important for translating a given word. So summarized, it would be assigning an attention weight to each word so that we know how much attention the model should pay to each word. So for each word, the network learns a certain context. So what is, for this particular word, what is the context of words that is relevant for translating this? So here's a figure from the paper outlining the whole mechanism in one slide. So one thing to notice is that there are 2 RNNs. So this is all my annotation, but this is what I got out of this figure. So there are 2 RNNs. First of all, they have a bidirectional RNN. We haven't talked about bidirectional RNNs, but it's a very simple concept. It's just running the recurrent neural network forward and backward, or you can also think of it running the recurrent neural network twice. One time in the regular order and one time by having the sentence put in the reverse order. So if we have the sequences or the input sentence x1 to xt, this is our input sentence. So one RNN runs this forward like a regular RNN from x1, x2, x3 and to xt. So it produces these hidden states corresponding to it. And then you can also have the same concept running backwards. So you just reverse the order. So this is shown here at the bottom. So you start with xt, then you go to x3, 2 and 1. So you're just going backwards essentially. So yeah, this is a bidirectional RNN. It produces these hidden states, and from the hidden states there will be these attention weights that will be computed. I will show you how that works in the next couple of slides, but here's just the overview. So we have a bidirectional RNN, then we compute these attention weights, and these go into our RNN that does the translation now. So I call this a regular RNN because it's not bidirectional. It's more like a regular RNN works, like we talked about before, except now that it also receives these attention weights as input. So not only the attention weights weighted, so here in this case, the attention weight weighted with this stuff here, so with this hidden state. I will show you how this gets computed in the next couple of slides. And then, yeah, it also receives the hidden state from the previous slide. So here, this is maybe a little bit confusing, but it's the S. The S is just a letter that they used to denote the hidden state of this other, of the second RNN, because here we already used the word, the letter H, and they didn't want to use the same letter, I guess, for here and here, because then it would be a little bit also confusing. So here, S is also the hidden state, but now the hidden state of the second RNN. And then these are the translated words. So here in this illustration, I'm trying to simplify, or at least try to explain what's going on in the previous figure in a little different way. So I haven't mentioned before what we do now with the hidden states of the bidirectional RNN. So when we have the bidirectional RNN, I mentioned we are running it forward and backward to obtain these hidden representations, but now we have 2 sets of hidden activations. One from the forward pass, let's call that F1, and at this point, and then we also have the backward one, let's call it B1. So how do we combine the two? So in practice, it's very simple. We just concatenate those. So we have just a hidden state that is twice the size of a regular hidden state from just the forward pass, because we are just concatenating those. So the concatenated, then let's call that H1. This is our hidden activation. And here I'm trying to illustrate how the attention mechanism works. It combines multiple things. It combines these hidden states from the bidirectional RNN and the activation, the attention weights. So these are the attention weights, and these are the hidden activations of the bidirectional RNN, and this is the hidden activation of the, let's call this decoder, decoder RNN. Okay, so for a regular RNN, what happens is that we provide the original word is input. If you think back of our word RNN at the very beginning of this lecture, we would provide the word x1 here as input, and then we, let's say, predict the next word. For the many-to-many one for language translation, we wouldn't have any input here. We would just use the hidden state from the previous time step when we are in the decoding part. So here, what's new is compared to a regular word RNN, where we get this x1, the word as input, we now take in a context vector. So this context vector provides information about the whole sequence, not just x1, the whole sequence, the whole input sequence. In a regular RNN, this would be encoded in the previous hidden state. So if we are at time step 1, this would be of course 0, but now imagine we are, let's say, at the 5th time step. So the 5th time step would combine in this hidden state all the previous 4 time steps. But it's like a very compressed version, and information might get lost. And for each word also in the sequence, different other words might be important, so it's kind of hard for a given time step to really ensure that right now it captures the important information for this current word, but then for the next one it captures other important information, so it's easy to forget what information was important from a previous time step and so forth. So to solve this problem, we have this context vector that allows us to take a look at the whole input sequence. So to illustrate this again, remove this annotation, we have this C1 here, and this C1 is computed by taking all the attentions multiplied by each hidden state, so these multiplied plus these multiplied plus these multiplied. So it might happen that a word is not very important. So in this case, if the word is not important, what would happen is that the attention weight would be, let's say, close to 0. Then it would not, let's say, use this word. Other words might be more important, so the attention weight is larger. And here's how the context vector is computed. It's summing over the attention weights alpha multiplied by these hidden activations. That's how we compute this context vector. Now, how do we compute this attention weight itself? I mean, we talked about the hidden activation, right? So the hidden activation is just a concatenation of the forward and backward hidden activation. Now, how do we compute this attention weight? So the attention weight is computed by using another neural network, for instance, multi-layer perceptron. So let's maybe, before we get to that, take a look at this current time step, S1. So what does the current time step get as information? So it gets as information essentially this information from the hidden state, hidden activations from the previous time step. And then we also have this hidden activation from the current time step, right, X1. So this is previous hidden activation of previous time step, and this is the hidden activation of the current time step. And this network here gets or takes both as input the information from the current time step and the information from the previous time step, and then outputs a score E. This is our unnormalized attention weight, and this unnormalized attention weight is put through softmax function to normalize it so that the attention weights sum up to 1, right? So after softmax, as you are familiar with, we would have, it should be over t, I guess. So they should sum up to 1. And yeah, so this is how we compute these attention weights. And yeah, there might be larger and smaller attention weights given how important each word is. So it's a form, well, the attention weight depends on both the current time input and the previous hidden state. So the attention weights might be different if we look at a different word. If we have maybe attention weights that say that this is 0.8, 0.1, and 0.1 for the current word for this context vector here. It might be different if we compute C2. It might happen that this word here, the first one, is not that important. The second word is more important, and so forth. So at each time step might be different words that are important. So, but yeah, the bottom line is that this attention mechanism allows the network to kind of get information from the whole input sequence at each time step, in addition to just this compressed information from this hidden state. Right, so to finish it up, here's another figure from the paper where they visualize the attention weights. Since the attention weights are values between 0 and 1, my guess is the white ones here correspond to a high attention weight of 1, and the black ones here correspond to a low attention weight of 0. So I guess this is a 1 and this is a 0 here. So here you have, actually no, I think they translated from English to French. Might be wrong, I might be misremembering. So let's say this is our input, and this is our output. And then you can see for each word how much attention the network pays when translating. So when translating, let's say the L here, it pays most attention to the, but also something to signed, and so forth. And you can see for some, like the number here, 1992, it really only pays attention, you can see that, it only pays attention to this number, which makes sense, right? So in this way, what you can see here is there's a strong value, attention value in the diagonal, which means that it's kind of like a one-to-one translation in that way, but not always. There are some cases where it pays attention to words that are also farther apart in that sentence. Right, so this is the attention mechanism, and in the next video we will build on this idea by taking away the RNN part, because it turns out that we just went from a very complicated model, the RNN, added attention, but actually we don't need the RNN at all. We can maybe also get good results with just attention, and that is the topic of the next video.